Alyosha has
Yes.
been an influential figure, really, in computer vision in general. I think most of us, definitely myself, my generation, when we grew up and went to CVPR, wanted to be like Alyosha. So really, it's an honor to have him here. He was advised by Jitendra Malik at Berkeley, now also faculty at Berkeley after being at CMU, and he'll be speaking about why it pays to read perception literature. Confessions of a Computer Scientist. So Alyosha, the stage is yours. Take it away.
All right. Thank you very much. Thank you for inviting me to speak here. So I'm the last talk, and so I'm going to keep it light. And also I am a computer scientist. I'm a computer vision scientist. I don't actually do any perceptual experiments, but I'm a huge fan. And indeed, I was thinking that I would do something a little bit different and just kind of look at all of the ways that reading, perception, cog-sci, psychology literature has shaped my career and kind of guided me in doing my work. Okay, so basically, yeah, this is going to be kind of a little bit of a rambling love letter to you guys. Okay, so I started with texture. This was the first thing that Jitendra Malik told me I should look into texture, and it was immediately I got excited because it is this magical problem that's not just a computer problem, right? It's a perceptual problem. So you have a bunch of samples that don't look like each other at all on the pixel level. It compute like L2 distance, they're all very different. And yet a human looks at it and they all look like they are drawn from the same distribution. Okay. And so even the definition of texture really is a perceptual definition. And things like texture analysis is basically really it's all about you have some true infinite texture out there in the sky, and all you have is you have a couple of samples or some samples, and then your question you want to ask is are they drawn from the same texture or different textures? And so really my first influence in psychology has been, of course, Béla Julesz, who is really the father of texture, and I mean, he also did the random dot stereogram thing, but I don't have stereo, so I don't care about that. But texture, really, he was really very influential for me. And so for those of you maybe who don't remember, he was really the one who focused on this idea of pre-attentive discrimination. So he noticed that there are some patterns that just pop out at you and are easily discriminatable from the background, and other patterns that are very hard to discriminate, even though in terms of ink differences, they are just as different. And so he basically argued that the things that you cannot distinguish pre-attentively are what constitutes the same texture. Okay. And so my first work was on texture synthesis, which is kind of a related question of if you have one sample from this infinite texture in the sky, how can you generate another sample that a human would think is drawn from the same texture? And we did a paper on this non-parametric texture growing, and we got some cute results. And one thing that kind of I found interesting is that by mistake, I ran it on an image that turned out not to be a texture image. It was like a real image, and this was like an extrapolation result. And I was kind of surprised that that worked. It still kind of worked. Okay, and then reading further, I happened upon, or maybe I heard it actually at one of the workshops. Simon Thorpe came and gave this wonderful talk on recognition, on visual classification, and I think the task was, is there an animal in this image? And he was doing it at something like 150 milliseconds, so really like pre-attentive, exactly like Béla Julesz's regime of pre-attentive, like feed forward, not much time to do anything really, right? And what Simon's lab has shown is that people were really good at this, like surprisingly good at doing what you would think is like a very fundamentally deep and a semantic task, and they were just doing it like nothing. Okay, and of course Nancy Cumbersher also did cool follow-up work in that, and kind of also reaffirmed these results. And so there was already this feeling that there was something about texture processing that was kind of more that meets the eye. And in my lab back when I was a grad student, Laura Walker Renninger and Jitendra Malik were looking at scene classification, and they were basically, their idea was to do some really stupid texture discriminator. And so what they did is they just did basically a dictionary of patches, and then they looked at the histogram of these patches, textons, and then they basically just did nearest neighbor in the histogram of patches discrimination. So really very basic, very low level texture kind of question. And they thought, how far can they go? How well can they do? And what they found on this kind of scene discrimination task is that they were, I don't have them. Well, these in the x-axis, there are different scene types like bedroom, forest, beach, etc. And what they found is that compared to human subjects, they were basically doing pretty well on the just on the texture. They were pretty much on the level of like humans at 50 milliseconds. Okay, and so this really got me thinking. And then later on, there was another work also on just doing texture. Notice this is 2001. Okay, and I'll just play this work from the Microsoft lab. So this is John Wynn and colleagues, and here they basically just they compute texture within this boundary, and then they just do kind of nearest neighbor in terms of the texton representation. Okay, so the stupidest, simplest thing you can think of, right? It doesn't know anything about the boundary of the cow. It doesn't even know about the whole idea of a cow. It's basically doing like cowness or grassness, right? It's totally doing texture recognition. But you show it to an undergrad, and we'll be like, wow, it's the computer is recognizing objects, right? And this really made me realize how amazing. I mean, look at this. Like, this is, it just works. And like, you don't even need the full byte. Like, it has no idea that this is like many bytes. It's not Y byte, right? But it doesn't matter because it looks good. And so this really opened my eyes, and I realized, a lot of what we think of as object recognition is really just that. It's really just texture recognition. And so when later on, there was all of these examples from Gaddis of neural networks. You scramble your image into some texture mumbo jumbo, and it just works perfectly fine. I wasn't surprised. To me, this was obvious because of all of this texture perception work that I have read about, 20 years earlier. And so this is why I was really focused on thinking about going away from just texture recognition and really thinking about scene understanding, right? Not just recognition, but really parsing the scene into some meaningful parts. And it is really all about learning complexity, because if you look at the kind of a natural scene, it's like you cannot do it without dealing with occlusions. You cannot do it without reasoning about 3D. You cannot do it without really trying to understand what is it that makes a scene. And luckily, I found that psychologists again were thinking about this. So, for example, Hock and colleagues were talking about different types of ill-formed scenes. So, type 1 is a well-formed scene, and then there is a bunch of different ways it can go berserk, right? And then Irv Biederman had this wonderful page. So, Biederman, of course, most people think of Biederman, they think of geons. And, I think psychologists are really into geons. Like, from computer vision perspective, I mean, they're nice in theory, but like, it's just impossible to actually do them in practice. the Biederman's work on understanding well-formed scenes, that's a beautiful paper. If you haven't read it, just beautiful paper. And so Biederman basically had this whole theory about what is it that makes a well-formed scene. What is it that you need to have for a scene to hang together, to be a coherent thing. And so he hypothesized 5 parts: support, size, interposition, and likelihood of appearance. And luckily, I was reading this paper, and I was also in Brussels, and I went to a Magritte museum, and I realized that Magritte apparently read Biederman, because he had all of these things in his painting. So here is a violation of support. Okay. Here is a violation of size. Here is a violation of interposition. And here just everything goes bad. Position, probability, size, everything. Okay. And so then I realized that really we need to deal with all of these things, and if we can get there, then we can maybe try to understand a scene. And this is what I convinced my very first PhD student, Derek Hoym, to take on, and he was super brave, because I thought that it was like a 20-year worth of effort, and he didn't know better, so he took it on, and he basically looked at trying to understand a 3D spatial layout from a single image, okay, and kind of try to figure out what is it that basically think about the 3-dimensional structure of the scene, like the support surface, the vertical surfaces, their orientations, and also connect it with occlusions, figure ground relationships, and also object sizes and interposition. All try to do all of this together. Okay. And of course, the main challenge is that from a single image, this is ill-defined, right? So given this image, it could be this, it could be this, it could be this, it could be an infinite number of interpretations. And the trick is, of course, to get the right one, to find the right interpretation, or the most likely interpretation, right? So, how is it that we can figure out that this is unlikely and this is more likely? And so, I'm just going to briefly summarize his work. And he basically talked about labeling these geometric classes of different types of surfaces. And then we had a way to pop it up like a basically paper pop-up, and given this geometric labels, kind of find where to fold and where to cut and make it into like a little very coarse planar 3D model, and then be able to kind of basically walk into an image from just a simple image. Okay. And it's a very coarse model, but it captures the percept of 3D in a way that a lot of the more complex, more sophisticated models do not. So here's some more examples of that. This is really old stuff. This is like 2005, but still cool. And it's an interesting kind of historical note that basically at the same time, Andrew Engen students were also interested in kind of understanding 3D from a single image. But they went a completely, quantitative route. They were basically predicting depth at every pixel. And I would say that the kind of the perception-informed view was, I think, was a more right way to go. And in fact, if you look at Ashutosh Saxena, who was the first author of this other competing work, in a couple of years, he actually came around to our view, and he basically added the qualitative 3D understanding to his system. So it was kind of a, we got ahead because we read more perception stuff. Now, this is not always going to work. So here is an example of things not working. And it's not working because the previous model did not really deal with occlusion boundaries. Okay, and so next Derek thought, okay, we needed to figure out, depth ordering and occlusions again in a qualitative way. And of course, then you have to go to all of the literature and figure it out. And of course, I made Derek read all of that literature and basically boundary ownership and all that stuff. And it's interesting again to kind of connect this to the old classic work in computer vision, something like the Waltz algorithm, where the idea was that you're going to label your boundaries, you're going to find your boundaries, you're going to label them, and then there is this beautiful, gorgeous junction propagation algorithm. For those of you who are in computer vision, I'm sure maybe you have, or in older generation, you probably had to do it in your class. So there is a different type of junctions, and then you propagate labels for the junctions, and you get this beautiful result out, okay? And it's a gorgeous, beautiful story, okay? The only problem is it just never worked. It worked on these, hand-drawn things. It never worked in the real world. And everybody was kind of puzzled, why doesn't it work in the real world? So people try to find all these T-junctions and then blah, blah, blah. And I just happened to stumble upon a little wonderful paper by Josh McDermott, which basically kind of made me realize we are just on completely the wrong track. So basically, he was looking at T-junctions in real images and looking at how people perceive T-junctions. And he showed that locally, from a little patch, humans could not tell T-junctions or any other kind of junctions, really. It was really only when they got the whole context, they were able to realize that those were, the correct type of junction. So what we were doing in computer vision was completely backwards. We were starting with trying to find junctions and then trying to understand an image from there, whereas it looked like the humans were doing it the other way around. They were first getting some notion about regions and boundaries, and then kind of the junctions were the output, not the input. And so that made us just go this direction. And so basically what we started with is going from edges to boundaries, and then trying to figure out which were the occlusion boundaries, in conjunction with also reasoning about qualitative depth and these kind of surface representations. Okay, and we were able to slowly kind of converge upon a representation that would give us both boundaries with a labeling of foreground, background, and also with a range of depths. Okay, and the final work of Derek's thesis was basically just put everything together with surfaces, occlusion boundaries, and objects and their scales, and basically put it all together. And it was actually very much inspired by kind of intrinsic image work from Barrow and Tenenbaum. So that was all fine, but the problem was that surfaces were just not good enough to really represent the scene, because they were just like all these paper cutouts. There was no meat on this thing, right? And so we realized that we really need to go from surfaces to volumes. Okay, and again, this is where kind of we were very much inspired by Biederman and colleagues, and we tried to basically figure out how to inject both geometric volumetric constraints and also physical constraints like stability, all in the same framework. And this was a work of Abhinav Gupta, who back then was just a starting postdoc in my lab. And so we had a kind of a very cute algorithm that kind of starts with little blocks and then basically makes these like Lego blocks, makes them to represent a given image, again from a single real image. And so we were able to do these kind of 3D parse graphs with relationships like in front of, above of, heavy, light, And again, this is like 10 years ago. I'm kind of surprised how well we were able to do, and we were able even to get a hold of some sort of like 3D renderings from real images. I think I have actually not seen any other paper that's able to do something like this. So this is still a hard problem, and I think we're able to do as much progress as we have because we were aware of all of this work from Irv Biederman and colleagues. At around that time, I had my kind of the next inspiration, and this one came from Aude Oliva. Okay, and this is her wonderful work on the capacity of visual memory. I know that Aude gave a talk here, but unfortunately, she doesn't talk about this stuff anymore. And the young kids, they don't know it. And so I'm going to make sure that public service here to make sure that everybody knows, because it's a beautiful, beautiful work. So, of course, in 1973, Standing already showed that humans have this amazing capacity for remembering images, something like 83% recognition of 10,000 images. Okay. But Standing was he did like forest versus beach, right? So it wasn't clear how much information was being stored in the memory. Is it just one label or is it like every pixel, right? And so what Aude did is that she basically redid this experiment, but really tried to push the humans harder by showing a lot of very similar objects, and also looking at the same object in different states, and also having similar classes of objects, but not the same instance. And the results were spectacular. So she replicated Standing result, okay, for kind of the same object class, but she also showed that even if it's different, if even people were able to distinguish one member of a class, like if they were able to tell apart one remote control from a different remote control, or they were able to tell apart different states of the same image. So it was just incredible how much we remember visually. Okay, and so this really was inspirational to my data-driven kick, where James Hayes and I, thought, okay, let's try to do something with lots and lots of data. We thought, okay, how about hole filling? So here is some thing we don't want. We are going to get rid of it in Photoshop, and now we are going to download 2 million images from Flickr, and this is 2007. So this is a long time ago, and we're just going to try to see if we can use some other image to fill in the hole, and ta-da, it actually works. And the cool thing is it works because of all this data. Okay, so because first James tried it on 20,000 images, which back in 2007 was like huge amounts of data, and it just totally didn't work. Here are the nearest neighbors, and they're not that near. But then he just kept downloading, and when he got to 2 million, boom, it just worked. And so here's some other examples. Yeah, and we also did it for geolocalization with the same idea. Okay, but do humans really remember every single pixel? I asked Aude when we were in Paris. We happened to be together in Paris on our sabbaticals in 2012, and we had a wonderful time drinking wine and talking about philosophy. And Aude was like, "Huh, funny you should mention. I actually have some experiment of this, but I didn't think anybody cared, so I never published it." So this is such a cool experiment, at least to me. I'm just going to play it. Aude gave me the slides, so we're actually gonna do it. Okay, I think I still have a little bit of time. So this, it's hard to do on Zoom, but so the idea is, Aude is gonna show you lots of images or a bunch of images. When you see the same image twice, you're gonna clap. Okay, it really works when you can hear other people clapping, but okay, here we go. Okay, so of course you notice that some of these images are basically just kind of random textures that don't mean anything. And when you do it in an audience, it's very clear. Basically, people do really well on normal images, and they are basically a chance on these random meaningless textures. It's a very, very clean result, very powerful result. And so this made me think, wait a minute. It's not just that you're remembering every single pixel. You're really remembering something that's meaningful to you. So you have you're remembering on some natural image manifold. Okay, and that really got me into this whole self-supervised representation learning. So the whole self-supervised learning, I got this idea from Aude in 2012 in Paris, and then like all of these papers that my lab has since put out, all result of this realization that we really need to learn a good representation that kind of that sits on the data manifold, because otherwise it's we're not gonna make it work. Okay, so do I have more time, or am I done?
You can keep going, Alyosha. Yeah.
Okay, let me just one last thing is there's all these self-supervised stuff. This is probably the one that may be most interesting to you guys. This is the work we did with Andrew Owens, and this was a self-supervised learning work, again inspired by a perceptual experiment, the McGurk effect. I'm sure most of you know. Right? So he's saying ba. Ba. Right? Now he's saying fa with an F, but actually the Aude is exactly the same. It's just that the video is different. Okay? So this is just a beautiful illustration of a very tight coupling between the audio and visual processing. And of course, in computer vision, we never does this, right? It's always separate. And so we decided we're going to do learn a joined audio-visual representation. And the way we did it is our usual self-supervised trick. We say, okay, let's try to bring the real ones close and the fake ones apart. So we say, okay, let's take real is just take a video and its corresponding audio, and fake. Oh, sorry. This is real. And fake, we just take some random other audio from some other. Okay. Now the problem is this is too easy. Not going to work very well, because it's too easy to tell. So what we did instead is we took the same audio, but we just shifted it a little bit. Okay, and then see, now the system needs to really work hard to try to figure out that there is a shift. It needs to find correspondences and figure out that there is a shift. And so we trained the system, and after several weeks of training, we're able to get a representation that was it knew where the sound was coming from. Okay, and we even did a little cute demo of separating on-screen from off-screen sound. So this is
we were able to show to the rest of the world the unshakable Japan-US alliance.
Thank you so much.
Thank.
And then we can just do only the thing that only the audio that has evidence in the pixels.
の揺れない絆を世界に向かって示すことができたと思います。Thank you so much.
Or we can do the other one.
Were able to show to the rest of the world the unshakable Japan-US alliance. Thank.
Okay, and I have many more examples, but I'm out of time. So in conclusion, in computer vision, I have this reputation. People say, oh, he's very creative, he has lots of out-of-the-box ideas, and frankly, this is all bullshit. The dirty truth is, I just read and get inspired by human perception research, and you can be too. And so this is basically that's how it is. So thank you, and also thank to all the wonderful psychologists that I got inspiration from. Thank you.